What if your lathe had a secret milling mode? Back in part 1 and 2, I've built and tested the spindle for my milling attachment. And now the main question is, how do we get from this to this, while tackling some major challenges on the way? It all starts with this mounting plate. Due to it being big and me not having a milling machine, I had it machined by an external vendor. And to mount the spindle, I decided to go for my trusty thread inserts again. But this meant tapping all the mounting holes first. Introducing this tiny spring-loaded tapping guide. So let's build it. First, I turned the outer body, drilled the hole, and then to my later surprise, I stopped recording. So now we have this. The outer body, a heat-treated plunger, a spring and a cap. Assembled, it looks something like this, and now the cap can be press-fitted into the body. And why is it so tiny? It is also designed to be used via a collect in my milling spindle as well, for future projects. So let's use it. First step, centering the hole, then replacing the drill with the tapping guide plus the M3 tab itself, and carefully repeat this process 5 more times. After that, I inserted each thread insert into the mounting plate. With the mounting plate prepped, I began building the connection point for the Flexshaft motor. The idea is to transfer the flex shaft's rotation through a keyway into a belt, and here's the solution I came up with. We start by turning the ODs first, and most importantly the clearance fit between the connector and the mounting plate. Next up is the OD for the M20 thread and a needed thread relief cut. Drilling and boring to size and test fitting it for the flex shaft. After this, the ID is bored to size, and in hindsight I should have gone for a press fit rather than gluing the bearing in. The connector is parted off and gets rechucked to clean up the backside first. The OD is getting turned down quite heavy to fit the OD of the flex shaft for a smooth transition between the two. Cutting such a thread by hand again almost broke me. M20 is definitely the limit for this technique, and I should just invest into a single point thread cutting attachment by now. Last step is the grub screw to lock the flex shaft into the connector. The next part of the connector is the shaft, which links the keyed flex shaft to the belt wheel through a small bearing. Once it's parted off, I move on to my questionable attempt at sneaking a keyway into this part. Drilling an off-center hole right next to an existing one sounded much more reasonable in my head. So let's see how it turned out. Maybe more RPM helps. Oh yeah, that does the trick. Back to my hand tools, I guess. But it fits. That's nice. Time to press fit it into the bearing. A little bit of retaining compound and letting it cure overnight. Fitting all of these parts together revealed one major flaw. It wobbles. And of course this needs to be addressed. My idea to fix this was to recut the shaft's OD in its assembled position to eliminate the runout, but currently my flex shaft motor is controlled via this foot pedal. Not ideal if you want to dial in a constant RPM. So let's change that. This is the switch which controls the speed, and I replaced it with a AC motor speed controller. And after some wiring, the controller is placed inside a new case, and voila, it's alive. And now it's time for the sketchiest setup of the whole build. I used my vertical milling table to place a high-speed steel cutter onto the center line of the shaft. And after some polishing, the runout was reduced by a lot. With the connector finished, it's time to build the custom belt wheels. For each arbor I needed a different ID, and I just used the parts itself as a gauge to test their fit. And after parting off the first one, the same process is repeated for the second wheel. Next up is drilling and tapping of the grub screws. I tried coating the wheels with liquid rubber to increase the surface friction, but this stuff is truly awful. It peels off, it doesn't hold at all when used with a belt, so not recommended. Back in part 2, I saved the spindle housing mounting holes for later. Well, later is now, and I really want to nail this one on the first go. My plan here was to place the housing into the mounting plate and use the threaded holes to mark their position onto the spindle housing. Meet the pointy screw thingy. With the housing clamped to the mounting plate, I used it to mark each position. And, to my surprise, it worked like a charm. I spot drilled each marked position and drilled through with a 3mm high-speed steel drill. Glue up time. I used the same Loctite 641 to secure the angular contact bearings in the housing. Slid the spindle shaft through and applied thread locker before tightening the locking nut from the back. After 24 hours, I retested the runout and measured 0.014mm. With the main body complete, I turned to the front cap to keep chips and swarf out of the spindle. I machined those parts off camera. The assembly of the milling attachment is quite straightforward. First, place all the parts onto the mounting plate. And once the Flexshaft Connector is in place, I secure the spindle with 3 M3 Torx screws and Nordlock washers, keeping them from loosening under vibration. Next up is the PU belt. I have 3 lengths to try, and I'll test under load later to see which one performs best. The mounting plate is fixed to the Shoreline vertical milling table, and then the flex shaft is fitted onto the connector. With the front cap removed, I insert the collect and tool into the Morse taper, secure them with the draw bolt from the back, and use my spindle lock to keep the lathe from spinning while I use the milling attachment. I also rigged up a quick, very DIY air cooling and chip removal setup. It's angled this way for now so it doesn't block the tool on camera. In real use, I'll point it down. And just like that, my lathe is also capable of functioning as a free-access drilling and eventually milling machine for my watch's main plate, other parts and the first gear. But that will have to wait for the next video.